1905, I said Einstein, he has related both E is equal to h nu quanta of energy with his equation E is equal to mc square. Now after that, after 1905, next came into picture de Broglie's relationship. That's in 1923. After 1923, 1924 was your Planck's derivation. Now what happened? This Louis de Broglie is a French physicist. What he said that just like light, he spoke, or he started using the word matter. Till now we've been studying light has wave nature, light has particle nature. Now de Broglie was a physicist, French physicist, who has used the term matter, and he said matter also possesses dual behavior, he said. So what is that? The same thing. Matter has wave nature and matter has particle nature. He could explain this concept here, both. So he is given a derivation, mathematical derivation for this. Let's start. Whenever you're writing de Broglie's relationship, the first important thing, start with the basic thing. Let us write the derivation. So we are speaking in terms of matter. Now E is equal to h nu. Okay, this is the first thing. That is energy of the photon. Now, according to Einstein's equation, the same thing. I'm taking the same and I'm further proceeding. E is equal to mc square. That's fine. The same concept. Now what is this? M is the mass of the photon. Now let us relate the same thing again. I'm writing the same thing. mc square is equal to h nu. mc, I can write this as mc square is equal to h c by lambda. Why did I write this? Because nu is equal to c by lambda. Same concept. Now take this here. Now we will rearrange. Till now we have done this in there also, isn't it? Now we will rearrange the equation. So when I rearrange the whole equation, I'm taking lambda out. Lambda is equal to this out. Lambda is equal to h by mc. Now what happened here? When you take this mc out, this c and the c gets cancelled. So I'm left with lambda by h mc. Now the same thing. What did de Broglie? De Broglie pointed out the same equation. Like he said, you can apply the same equation to material particles also. So what did he say? Instead of using m for the mass of the particle, instead of we can use it as mass of the particle instead of mass of photon. Right here we have got h by mc. Now he said the same thing, because he's speaking in terms of matter, isn't it? He said using m for, I can write m as mass of particle instead of, I can write instead of mass of photon. You can use this. This is what he said. And halfway he said c whatever is there. He said your c, h by mc I got, isn't it? Now he said c, that is velocity of photon, by nu. This is your velocity of photon. You can replace this by nu. So what can you write? Lambda is equal to h by mv. This is your equation. Now this equation is called, instead of h by mc, h by mv, this is called de Broglie's equation. De Broglie's equation. Okay, yes. So now I can write the same. Lambda is equal to h by p. What is p now? P is called momentum. Momentum. What does it depend upon? It depends upon p is equal to m into v. This is your concept, isn't it? Right. So this is particular thing. Now this de Broglie equation, the way, what did he say? The waves whatever are associated with the material particles or the material waves. Now here instead of particles you will be using matter waves. These are also called as matter waves or de Broglie's waves. You will not use particle, nothing. Matter waves or de Broglie waves. This is a simple change in that. Right? So let us see the significance of de Broglie. So when I have to speak about the significance of de Broglie equation, let us write the heading, significance of de Broglie waves. Okay, let us write small and de Broglie waves. Let us underline this. So when I have to speak about the significance of de Broglie waves, so basically you have to be just clear about the concept here. Right. So here one thing he has calculated, will calculate between a large mass and a small mass and see. Let us see, let us apply the de Broglie for a large mass. Here I am taking for a small mass. Just see. Now let's take a small sum and see. Let us consider a stone. Okay, I am considering this one. Here I am taking large mass as a stone. Here I am considering an electron. Then I can see how is it applied. A stone of mass 100 grams. Okay, now this is moving with the velocity of 1000 centimeter per second. Okay, now let us calculate lambda is how much. Now here in this case I am talking in terms of your electron in hydrogen. This is a small mass, isn't it? So we'll talk in terms of electron. I'm comparing between the large mass and the small mass. Electron high, first of all, hydrogen atom is very small. In that I'm talking about an electron, right? Fine. So I need to calculate lambda in this case. So when I take both the concepts here, lambda is equal to h by, this one isn't it, p, that is m into v. How much is Planck's constant? It is 6.62 into 10 to the power of minus 27, divided by how much is the mass given? 100 grams. This is the mass given, isn't it? So 100 into what is the volume given? It's nothing but 1000. When I solve, I get an answer of 6.62 into 10 to the power of minus 32 centimeters. Fine. This a bit. Now if I have to calculate here in this case for electron, okay, first let us write what is the mass of electron. It is 9.1 into 10 to the power of minus 28 grams. Right, so here the frequency 2.18 into 10 to the power of minus 8 centimeter per second. Lambda, if I calculate both h into the same thing, if I write into v, I get an answer of 3.3 into 10 to the power of minus 8. Okay, now why am I doing all this? Just see. When I compare this value, mass of the electron, with this value, so it's almost very negligible, isn't it? Very small compared to this lambda. So detecting too small, hence the detection of this one too small will become very difficult, isn't it? Yes, so that particular thing, so that's why he said always consider the matter in the form of, so property of large object is like property of the wave. This wave, this is for the wave, this is for the electron, which is very small, which cannot be detected. Fine. Now here I am going to apply your de Broglie or application of de Broglie to Bohr's theory. Why am I taking this concept? Because Bohr always said the electron or it moves in, or it rotates in circular orbits, and the orbits are fixed. What are the shells? Those are KLM shells, isn't it? Right. So I'm going to apply Bohr's Bohr's theory, de Broglie's equation to Bohr's theory. So here we are going to learn a term in phase and phase out. Okay, let's see what it is. So I said according to Bohr's theory, what did he say? Whenever you have an atom, you have fixed shells like this, K, L, M, N in shells, isn't it? These are the fixed shells. So electron always rotates in this fixed shells, K, L, M shells like that. Fine. Now he said only electron, that particular thing, it rotates in that orbit which has an angular momentum mvr. Okay, so what did he say? Once again, he said electron or an atom can accommodate electron only in Bohr's orbit, whose circumference, how much should be the circumference? It should be 2 pi r. Correct? Now let's see. mvr is equal to nh by 2 pi. Now I am multiplying this. 2 pi r is equal to nh by mv by mv. Okay, I've taken this side, this and this side. Right. So we have one more formula, isn't it? That is h by mv. What is lambda is equal to h by mv? We have got it from de Broglie's equation. I am applying de Broglie's equation to Bohr's. This is what is your Bohr's, isn't it? It is quantized, he said. Now I am applying this in this. 2 pi r is equal to nh by mv. H by mv is what? So I should not write this, I should only write lambda. because I've substituted this one, the Broglie's equation in both this one. So this is one important formula. Now when I have to take, see, the electron is moving, the electron in the Bohr's orbit is moving in the form of a wave in this, isn't it? This waveform, correct? Yes. Now there's something called if the electron wave out of phase. So here this is so you're getting wave moving in the direction, and that is wave out of phase. This is called wave out of phase. Right? Now, why I'm explaining this concept, I'm not done clearly, but see, why if the circumference is bigger or smaller than n lambda. Now this is your 2 pi r circumference, isn't it? Now, if the circumference if it is bigger or smaller than n lambda, what will happen? This wave train will go out of its phase. It will move out of phase. If it is only 2 pi r, it will move like this, in this direction. But if it is this, let us write that the circumference, if it is greater than n lambda or if it is lesser than n lambda, it will start going out of the phase. We call it as wave train. We go to the phase, and what will happen? There's something called destructive interface of waves causes. We call it as destructive interface. So because of this, what will happen? It will start radiating energy. So radiating energy. This starts radiating energy. Fine. So this is how I've applied the Bohr's concept and the de Broglie's formula. So see, when it goes out of phase, automatically let's start emitting or radiating energy, isn't it? Right. So with this, we've completed de Broglie. Now let's come back and learn Heisenberg Uncertainty principle. Right. So after de Broglie's equation in 1923, that was 1923, isn't it? Now comes your Planck's quantum theory. So basically in your textbooks or something, they'll give Planck's first and then go to de Broglie, but I went with the year. So this was introduced in 1924. So here he started speaking about black body. What if we study? Whenever you're heating a black body, I'm taking a black body, when this is heated, what will happen? It's going to, I said, it's a perfect absorber as well as perfect emitter also, right? So this starts emitting thermal radiation. Emits thermal radiation. This is what we studied. Done. So here, this thermal radiation of different wavelengths. Of frequency. This is what we have studied, isn't it? Now, when we say this particular thing is a perfect, he said it's a perfect radiator and the perfect absorber. Now, this energy is discontinuous in small packets of energy. It's going to emit this radiation in bundles of energy. Bundles of energy or small packets of energy. So, this small packets or bundles of energy are called quantum. And when you say this bundles of energy, when we speak in terms of light, okay, let us write that as light. When we speak in terms of light, we use the term photon. For light as photon, for bundles of energy as quantum. If it is many packets, then we call it as quanta. Then he said, suppose if I take the same Planck's constant, he has introduced, or he said, using that quanta, he has given the formula E is equal to h nu. What is h equal to? H equal to 6 point Planck's constant. Let us write. H is called Planck's constant, which is equal to 6.626 into 10 raised to minus 27 ergs per second. If I write the same in joules, 6.626 into 10 raised to minus 34 joules per second. Right. So this is what Planck said. Then he said, whenever a body is absorbing or it's radiating energy, so how does it do? It does in whole number multiples of quanta. So this is the term which is used. A body radiates or absorbs energy in whole number multiples. of quantum. Okay, what are they? That is NH or NH, 2NH or 3NH in that way. So what is N now? N is a positive integer. I'm talking about this one. N is a positive integer. That's it. So this is a simple Planck's quantum theory. Let's come back and learn your Heisenberg uncertainty principle. Right. So we have learnt the Einstein's equation 1905. Then we came to 1923. That was de Broglie's relation. Then 1924 we came to Planck's quantum theory. That is E is equal to h nu. Now next came into picture Heisenberg's uncertainty principle. This was basically introduced by Werner. Which year? It was 1927. Right. So what did he give? Basically he has given a relationship between this is what is important. This relationship between B by W means between two important things. A pair of conjugate properties. I'll tell you what are they. A pair of conjugate. What is conjugate? Conjugate means together properties. What are these conjugate properties? He basically spoke about position and momentum. These two are conjugate properties. Position and momentum. Both are conjugate properties. Now he said, this is your definition now. What is that? He said, it is impossible. Try to start with this word. That is what is uncertainty. Okay. It is impossible to determine position and momentum. Position and momentum. That means impossible to determine position and momentum simultaneously. Both I can't determine at the same time. Simultaneous position momentum simultaneously. Okay, of an electron. Okay, right. So this is what is the concept. What is the definition he said? What is the derivation he's given us? He has given delta x. Okay, that is position into product of delta p. What is p? Momentum. Position, this is momentum, greater than or equal to h by 2 pi. This is what is your uncertainty. Now the same delta p, since what is delta p equal to? Mass into velocity. I can write this. Delta x into m delta v is greater than or equal to h by 2 pi. Okay, let us see what am I trying to explain. So let us take two things. The same concept, let us see in terms of a numerical entity. Now, for a moving ball of iron, okay, there's a moving ball of iron, weight, mass of this is 500 grams, okay, right. That is one different concept which I take. Now the second concept which I'm going to compare is this for the same electron. Now I'll take it for electron. Okay, let's see. Now if I have to just write this for a mass of iron ball, this one, same thing I'm writing. Delta x into m delta v greater than or equal to h by 2 pi. Okay. Now delta x, I can write the same or as into delta v. Okay, I am taking this mass here. Greater than or equal to h is how much? 6.6 into 10 to the power of minus 27 Planck's constant. 2 into pi value is 3.14 into how much is the weight? 500 grams. This is approximately how much? It is 5 into 10 to the power of minus 31 ergs second per gram. Right? This is this. Now, what happened? Uncertainty, like this one, of uncertainty is negligible, isn't it? In case of large object, this uncertainty what is produced in terms of large object is really negligible. Such a big number it is, isn't it? So, what can we write? Uncertainty in measurement for a large object is negligible. Now, if I go with an electron, what is the mass of electron? 9.1 into 10 to the power of minus 28 grams. Minus 31, not kg also. Same thing, delta x into m delta v is greater than equal to h by 2 pi. Now, I'm sending this mass here. delta x into delta V is greater than or equal to 6.6 into 10 raised to minus 27 divided by 2 into 3.14 to 9.1 into 10 raised to minus 28 grams. Now, this is approximately 0.3 ergs second divided by gram. Now, this uncertainty delta x is very small, isn't it? This delta x value is very small. But when this uncertainty of small, when I take this delta x is small, but when this is small, delta will become very large. Vice versa. If delta V is large, delta X is very small. So this is what he tried to prove. Uncertainty measurement, both position and momentum are very difficult to or you cannot. So if this is high, this will be low. This is low, this will be very high. Simultaneously, you can't predict the position, momentum of an electron.